Come on in, everyone. They let people in. Feel free to ask me questions. I'm just getting my good notes ready. Lots of stuff happening. I gotta make a new page. I've got my good notes page made so I can write your notes on here. No one has any questions? Remember, feel free to speak out. You just have to unmute yourself, of course. I apologize for the awesome looks of my room. I have a guy who's a friend of mine is building my custom library cabinets, and it's taken a little longer than he had promised. So I got all this mess behind me. All my books are down on the floor, actually in two different rooms because it's the libraries back there and this is my office. So got a big mess. But I think it's going to be awesome once it's finally done. I have place for almost all of my books, probably. Of course, I don't know how it'll fit in. If I bring my books from my office, those of you who have been in my office, it'll probably seem how bad that is.
What's your favorite novel?
Probably A Prayer for Owen Meany. I think that's my best.
What's that one?
A Prayer for Owen Meany by John Irving. Actually, I'm a big John Irving fan anyways. So like I could put World According to Garp on there. That's another one. Cider House Rules is another one I like. I have some Margaret Atwood's novels that I like. I don't get to read very much fiction, but when I do read fiction that I've read about as things that most people read when they were in high school or college, because I was a loser all through school, and like by the time I graduated high school, I only read 3 books. So and that's like counting all my textbooks and everything, because I never cracked them or anything. I only remember doing homework through 5th grade exactly one time. So yeah, I was a loser, but I'm trying to make up. I think I'm up to 230 books now that I've read. Most of the ones you see back here are physics related. There's a great biography since the movie's coming out about J. Robert Oppenheimer. It's by Kay Bird. It's called American Prometheus. I highly recommend that book. Of course, that's nonfiction. It's biography, but really, really awesome. Another one that's really good is Quantum, something like Quantum. That's got a subtitle like The Fight for the Understanding of the Universe. That one's really, really good. And I'm trying to remember the author's name, but that's another. It's not really it's sort of a biography of a bunch of different people, because it tells us information about all the big scientists, but it tells us about a beautiful debate that Bohr and Einstein kept having at one of the Solvay conferences. Solvay. I think it's pronounced Solvay. I've been teaching myself Latin, so every time I see a V, I pronounce it as a W now. So I'm a little bit more stupid in multiple languages now. What's your favorite? Was that Jerry that asked?
Yeah, I'm just curious, whether you're a sci-fi guy or whatever. I think I haven't read a novel for fun in years, unfortunately. It's like everything I always read is something like
a white paper or something you got to do for work.
Or not a white paper necessarily. I'm not that speed, but yeah, basically some kind of technical thing or whatever. At least when I was in the Navy, it was always Or I would dabble in, leadership books, or because it's kind of comes with the stock and trade. But I have to say my favorite novel of all time was Slaughterhouse-Five, which is kind of a sci-fi novel,
Yeah,
from Kurt Vonnegut.
yeah, that's on my list.
It's just a real fun read. That's why I liked it.
Yeah, and I like Vonnegut. He's pretty cool. Breakfast of Champions was pretty good. It cracked me up. I also love Twain. So if you ever read no, it's Connecticut Yankee and King Arthur's Court. That book is hilarious. Sci-fi would actually, I never really got into sci-fi, which is sort of a shame because now when I read certain sci-fi things, I love it. Like I mean, this is obviously almost sort of the antithesis of sci-fi, but still sci-fi was Hitchhiker's Guide to the Galaxy. I love that series. I've read, in terms of sci-fi, I've read The Martian Chronicles, and that's just about it, to be honest with you. I really should read more. I read Contact, and that was obviously sci-fi. Forgot about it. But yeah, and I like that book too. It was really good. The movie is good too, and actually it was a fairly faithful representation of the book, not the movie. So I was happy with that. Anybody else have any cool books they recommend? I have a list of books that I need to update because I stopped updating them just before the pandemic, but it's basically the list of all the books that I've read. I started making it up mainly because I needed a place to keep all the titles. If I'm reading one book and it mentions another book, then I often will go and read that other book. That happened because I'm a John Irving fan. That happens a lot with him because almost all of his main characters are always in teaching or something like that, and he's from a place where they have a lot of private prep schools and stuff. So whenever he mentioned something they were reading, I knew it was sort of the cream of the crop. That's how I got to read Silas Marner, The Great Gatsby, some other books too. But anyways, John Irving gave me a pretty good list. And then, like I said, if I'm reading something that Thomas Jefferson wrote and he mentions a book, or James Madison or something like that, then I'll often pick that book up too. I have Tristan Shandy, for instance. That was evidently Thomas Jefferson's favorite book, which is quite funny because you don't picture him as having that much of a sense of humor, but the book is quite funny and pretty fun. Well, it looks like it's 10 o'clock, so we should get started. Anybody have any homework questions? And by the way, your test is due tomorrow at 11:59 p.m. So don't ask any specific questions about it, or mention it, of course. I also mentioned, just in case Connie's here, and yeah, trying to see who else here. I mentioned specifically that you can access your test questions from the midterm after you've completed it, but it normally leaves it open where you can just see it with the wrong answers, or with the answer you chose and whether it's right or wrong. That's normally able to be seen immediately afterwards. Has anybody had any luck with looking into that after they took it? Okay.
No,
Well,
it was not available.
I'm wondering if that's because the way I set it up this time where y'all could actually see the correct answers. But obviously, I don't want that getting out until everybody's done. So that won't happen until all the tests have been turned in, completed, which should be by 11:59 tomorrow night. So like literally 12:02 or something in the morning on the next day will be the time that the test opens back up. If at that time, whenever you do go to check it anytime that day, let me know if you can't access it then, because like I said, I do have it set to where you can review it. You're welcome to. I allow it for you to take electronic, photographs or whatever of the midterm, so you'll have it to study by. Just ask you, as I did in the email, is on your honor, please don't share that with anybody. I don't even care if you, like, if someone in your class said, oh, I forgot to get that, or my computer didn't work or something like that. You're welcome to share it with another person in the classroom. I'm just asking that you guys not pass it on to any future students, just because there is literally a limited number of physics problems that can be solved. And eventually the universe is going to become such that maybe students do a lot more problems that are computers, using computers either to make the solutions, to work out the problem, or stuff like that. So, but until then, we really don't have a lot of problems we can solve in the way that I do, you know, theoretically with symbols and stuff like that, or even just numbers. So that's why I try to not let that stuff get out, and that's why I don't post them on my practice tests. But by all means, definitely get you a copy now, but just don't give it to anyone. It's sad, but sometimes people realize too late that they harm themselves, and even in not illegal cheating, but just looking up answers that they're allowed to look up, that can sometimes be a problem. Yes, it is Wednesday, 11:59. Thanks, Nathan. Yeah, I was thinking today was Tuesday, but no, today's Monday. So yes, so the test is not due tomorrow. Sorry about that, everybody. It's due the next day. I hope I didn't give anybody a heart attack. Thanks, Nathan, for calling me on it. Oh, yeah, Michael Crichton, yeah. I haven't read Prey, but I do like Michael Crichton. Okay, so last time we were talking about this new paradigm of ways to solve physics problems, and it actually built a whole different genre. There's all, you know, different ways where people start attacking a problem from something that looks nothing like the problem. Quantum field theory is an example of that. They just minimize this thing, and the minimization is a process where you minimize an integral figure, and ultimately that allows you to, in some sense, minimize the integrand as opposed to the actual integral itself. And you get, for instance, Lagrange mechanics, or you can get the Schrodinger equation, all sorts of neat things like that. So that's all where this can go. So that's kind of interesting. But what I thought I'd do now is I want to make sure we solve some very specific problems from the chapter on conservation of energy. And I got to introduce the work energy theorem. And what I'm doing is I'm going to also show you another instance where you can take the derivative, remember the gradient of a scalar function that happens to be an electric potential or some other kind of potential, gravitational potential, for instance. If you take that quantity, you can take the gradient of it and then multiply that gradient by a negative, and out pops the actual force or the electric field or whatever. So I'm going to give you another example like that as well. And next time, I might start it this time. I doubt it, but I might start chapter 9 as well, which is the chapter on momentum. Okay. So again, anybody have any questions before we get started? I've let a couple people in since I last asked that, so I want to make sure I give everybody a chance. Nope. Also, I've got a lot of people that are coming in like multiple times, so I guess you're getting kicked out or something. Hopefully that's working out. All right, so feel free to just speak out if you're missing something. If you don't have an audio system, so you can then you can just use the chat. You might need to keep an eye on the chat with me though, because sometimes I'll get in my own little world here and look at my iPad and not keep up with the chat. So if someone sees that someone posted a chat that I need to answer and you let me know, that's cool. I appreciate it. I'll try to keep an eye on it and always keep it open, but when I switch, it's in a weird place on my desktop. So, all right, well, let's get crack-a-lacking in. So I told you about those, one of these things is true. That means all these things are true. And that's sort of a big deal. One of the things was that, for instance, there exists a scalar function u such that the force is equal to the negative gradient of u is a case in point. So I'm going to start off by solving one of those problems. And to do that, I've got the share my screen. I've been watching Caddy K this morning. She's from Great Britain, so now and then I'll accidentally slip into a British accent, which I don't have. So it's a gift, really. All right, see how long this takes.
Sir, while you're doing that, can I ask a quick question?
Yeah, go for it.
So you made the lab 3 due at 12:45 this morning. Can you open that back up, or?
Yeah, I will. In fact, I thought I had made it to Wednesday morning, but I'll at least put it back to Wednesday morning at 12:45. So actually, that's Wednesday afternoon. Yeah. Who was that asked that? I didn't recognize the voice.
That's Etau.
Okay, gotcha. All right, that's you. Okay. So let's imagine, for instance, that we have a scalar potential. Specifically, the scalar potential is U equals, I don't know why I'm writing in red, but here we are. So U equals negative A times X over B squared plus X squared. Now, this might seem kind of odd and made up, and in some sense it is made up, but it also has a very close form to a specific electric potential you'll get for a very specific problem in electricity and magnetism. And I suspect if I worked it out, I could probably get the same sort of potential for gravity as well. So this is actually a real potential. It's just you're not where you necessarily get it at this point. So what we know is, according to the, I'll just write the question here. So according to the book, there's supposed to be, in that mathematical stuff that I told you, there's supposed to be a scalar function that exists as long as the vector function, which in this case we're talking about as a force, was conservative, which meant the curl of f is equal to 0. So in this case, what we're going to do is we're going to work out what that is. And according to that document, it said that it's the negative gradient of the u gives you the f. This one only has one variable in it, x. So we're going to assume it's basically just one variable. And in this case, we're actually talking about a force that happens to be in the x direction. So here's the solution. F is supposed to be the negative gradient of u. So you could also write this negative gradient u if you wanted and put a vector symbol over it. Normally, everybody just recognizes this triangle as a vector quantity. In typeset, we just use a bold print, but I've never really taken any time to ever write an arrow over del or del u or anything like that. So it's important for everybody to know it's a vector, and you're never supposed to have an equation with a vector on one side and a non-vector on the other. So do keep that in mind. Just you might just recall that this is a case where everybody should know it's a vector. So what we're going to do is we're going to take the derivative, because the gradient operator is actually defined to be I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z, which before I've actually written, just to make it more succinct, I've written these derivatives like this in the past, and that's not uncommon within the vector calculus mathematics world. So just keep that in mind. So what I'm going to do now is I'm going to say f sub x is equal to the negative, let's do a partial of u with respect to x. So just the x component would be getting that that partial with respect to x part and leaving off the I hat, because we're just saying it's a component. So when I do that, I get negative partial with respect to x of negative ax over b squared plus x squared, like that. I do not memorize the quotient theorem for derivatives, but I know how to do it because I've derived it before, and that's what I do, is I just pretend like this is multiplication. So I'll show you that in a second. All right, what am I going to do? So what I'm going to do is I'm going to say this is the same thing as, I'm just pulling that negative and the a out in front because that part's clearly a constant and can be pulled out. I'm going to say the partial with respect to x is what I'm trying to get. But in this case, I'm going to say it's x times b squared plus x squared to the negative 1 power. So basically, I have a product rule, which I always remember, and I don't have to, make up a song to remember the quotient rule or anything like that. I just work it out this way. So when you're doing a product rule, you take the derivative of the first factor, which in this case is x. So I'm going to say partial of x with respect to x is just 1. So now I'm left with b squared plus x squared to the -1 power. And we also, of course, multiplied that by 1 because the exponent on x was 1, but obviously that doesn't matter. Now I've got to do plus, and actually I'm going to go ahead and pull this a out in front of everything by putting some curly brackets here. Now I'm going to take x and just write it down, but now I'm going to take the derivative of b squared plus x squared to the -1. We know that'll be -1 times b squared plus x squared to the, in this case, we subtracted, so -1 minus 1 is -2. And now I've got to use the chain rule, which is taking the derivative of b squared plus x squared with respect to x, which of course is going to be 2x. Okay. So now I can get that this is equal to a over b squared plus x squared plus, or excuse me, minus, because that -1 made it minus. It'll be minus 2x squared over b squared plus x squared on the bottom. Now we can get a common denominator, and that might make life a little prettier. So we could do that. Let me do it. I'm going to multiply the top and bottom by b squared plus x squared. And that's going to give me a b squared plus a x squared over b squared plus x squared to the 2 now. And this is minus 2x squared over b squared plus x squared, again to the 2 power. And when we do this, we're going, I'm really drawing my 2's small today. And now we have a common denominator. We can actually say this is a b squared plus, oh, there's supposed to be an a in here too. Everybody recall that I had the a out in front. I didn't distribute here, so I'm going to stick it right here. Hopefully y'all might have noticed it already, but just in case you hadn't, I'm glad I caught it now. I was just checking my chats too, just to see if anybody caught me on that, because it would have been good. All right, so ab squared plus ax squared minus 2ax squared. All of that is going to be over b squared plus x squared to the 2 power. I can see that 2ax squared subtracted from ax squared just gives me positive ax squared, or gives me negative ax squared. So I can actually factor out that a again. I'm just going to say a times b squared minus x squared over b squared plus x squared squared. And that is f sub x. We are done. To be honest with you, we were done at this point right here. A lot of it is just when you're trying to solve physics problems, you want to make sure your answer is consistent with an answer that you've seen, or the answer that you think is the right answer. So that's me working it out. And in fact, if you look, there's an example in your book. Actually, let me look up what example number that was. Example 8.2 was that example, and actually they got exactly the same answer I did. So that's kind of a nice way to do it, and that's the way you should be doing your physics. That's why, one, we used to never assign homework, and two, we certainly didn't pick it up, or we would assign homework because we recommend certain problems be done, but we wouldn't take them up or grade them or anything. but the main thing is when you're doing physics or engineering or science, at least the more mathematical and physical sciences, you should, of course, always look for right answers when you're working through the problems to get to verify whether you did it correctly. And that's where the learning comes in. It's not from, it's not from me lecturing. There's some of that in there, but to be honest with you, the vast majority comes from your ability to solve problems of various types. Anybody have any questions on that particular problem? Okay, so I went ahead and labeled that as example 82. No one has any questions about anything on that? I'm going to move on. If you look at section 8-2-5, that's where they cover the gradient or the Nabla operator, the del operator I just used. They show you that, so you can check that out on your own in section 8-2-5. I'll just write that down here. Okay. So I'm looking for some other problems. What we might want to do, for instance, I'm going to go ahead and introduce you to something called the work energy theorem. And the work energy theorem just imagines us trying to compute the total work done. So let's say work is equal to the negative, or excuse me, shouldn't say negative here. Work is equal to the integral of f dot dl. If you talk about work total, then you must be talking about the summation of all the forces dotted with dl. In other words, remember I put that sigma on there to indicate this is what goes on the left-hand side of Newton's second law of motion. So that also means that Newton's second law of motion can be used. So I end up getting that work total is equal to the integral of m dv over dt dotted with dl. I think you realize though that dl over dt is velocity, so that's going to be equal to the integral of m v dv. In other words, when I group together this to make dv dt, then I can now use the dv as the integrand, and that dictates that the integral of m times v is just equal to 1/2, is just equal to 1/2 m v squared, and I evaluate that from initial to final. So work total, what your book is also calling work net, is equal to 1/2 mv final squared minus 1/2 mv initial squared, which is really just delta ke. So that's the work energy theorem. Okay, so that's the work energy theorem, and it basically just says, hey, if you add up all the work that's been done to something, that will give you how much the kinetic energy has changed. So in the sort of one of the extreme versions is, I know you guys were with me on Wednesday during class, and you left somewhere around 1-ish or 2-ish or something like that. And I know since then exactly how much work has been done on you. The total amount of work that's been done on you since you were last sitting in my class is clearly 0 unless you're currently walking while watching my video. Because of course the answer is just the change in kinetic energy, and the change in kinetic energy from you sitting still and then you sitting still again is 0. Therefore, the total work done on you since that time has to be 0. So that's kind of a neat little sidebar. But the main thing is now we have an idea of another way to solve problems. In fact, they often use this, or sort of the most frequently used example for the conservation of mechanical energy, or in this case the work energy theorem, is really in taking up a car just before a car wreck or something like that. So if you were, for instance, say a police officer and you were assigned to figure out what happened in a wreck, one thing you want to know is how fast the people were going when they had the collision, because it could be a speeding issue. And the way you could do that is they'll go out and they'll measure the actual skid marks. Well, the skid marks are where your tire has actually stopped spinning while the car has continued to move at ever slower velocity. So if you can calculate the friction work done, then that'd be the total work done on the car, would be basically the integral of the friction force dot dl. And you just set that equal to the final kinetic energy minus the initial kinetic energy. Obviously, the friction force will be a negative, so it'll come out as a negative number. And the final kinetic energy will be the car sitting perfectly still, so that's 0. And then we'll get equals 1/2 times the mass of the car times the square of the velocity the car had before the skid started. Now, if the skid stopped abruptly when it actually touched the other car, then you'd be off. You just know how fast the car was going. If you could figure it out, how fast the car was going when it hit the other car, then you could actually figure out how fast they were going beforehand. But it's a little more complicated when the collision interrupts the actual skid. So your book also makes a point, which I did too. I just want to remind you that where you consider the 0 potential energy to be is irrelevant. Really, when you're dealing with potential energy, it's the change in potential energy that really matters. So let's look at an example like the one in your book. This is like example 3. It says, if the original height of the rock shown below is y1 equals h is equal to 3.0 meters, calculate the rock speed when it has fallen to 1 meter above the ground. Okay, so basically all we have in this figure that they're talking about is really just this is figure 8. So yeah, it's really just a guy standing on a stool like so. And holding a rock. Like this. And what we're seeing is they're kind of a little wishy-washy on the diagram, so I'm not going to be as wishy-washy. I'm going to imagine this bottom edge of the rock that's also in equilibrium, so it won't twist as you let it go. I'm going to say that distance right there down to the ground is y1 equals 3.00 meters. I actually added an extra sig fig because the book was using just 3 meters, and then the other one was 1 meter. So no, they both had 1 decimal place. So I went ahead and switched that in 2. So that's our y1. What we want to know is when this height right here, let's call that, instead of y1, let's call that y. Whoa, no, let's just erase it. That'd be great. We'll call that y2. So y2 is equal to 1.00 meters, and that's where we wish to know the speed. Okay, so with conservation of energy, you can use the formula that I gave you guys, which again, this is not one that's in the book, but it is one you're allowed on your equation sheet. And it basically says that potential energy initial plus kinetic energy initial plus work in is equal to potential energy final plus kinetic energy final plus work out plus E loss. And to be honest with you, you can put E loss on the other side too if you wanted to be more symmetric or something. It doesn't matter. The main thing is you're trying to account for another action, like some work put in or something like that. So whatever you do for E loss could have been done for work out as well, or could be E input on the left hand side would be another term you could add, but you could also still include that in work in. So this equation as it is good. It's something I've used since I've been 18 years old, and I found it helpful. So you can soup it up if you want to add some more terms. The main thing is just make sure you count all the ways energy can be transformed or lost. And as long as you count them all and count them exactly once, everything will be good. So with this in mind, I'm not really having any idea of work going in. There's no one pushing the rock, or no kind of forces yanking on it other than the gravitational force, which will be handled by the potential energy. And the person apparently is going to drop it from rest. So I'm going to say the initial kinetic energy is 0. I'm going to say the work in is 0. I could choose to call the 0 of potential energy the floor. And this is what we were talking about just a second ago. I could say this is U equals 0. Or I could say that spot is where U is equal to 0. I'm going to stick with the first choice for right now, but I'll regroup and show you what would happen in the case of using the other one as the 0. So at the end, the potential energy, since it's going to be 1 meter high, is not 0. The kinetic energy at the end is definitely not 0, but we're also not getting any work out. It's not compressing any springs. It's not pushing anything. And we're ignoring, air resistance and frictions and stuff like that. So all we have left now is mg. So this is our solution. Our solution is mgy1 is equal to mgy2 plus 1/2 mv final squared. And that final is the final that I'm saying is occurring at y2. So when I do all this, I can actually make it quite simple. For starters, I can say, bring all of the mg terms to one side. That'd be m times g times y1 minus y2 is equal to 1/2 mv final squared. And now you could notice that since the mass is not going to be 0, you certainly could divide through by the mass, and that would actually show you that this result is going to be independent of mass. And in fact, the result might even look familiar to you from your kinematic equations. You're going to get V final is equal to 2 times G times Y1 minus Y2 and square root of all that. I think you should recognize this as more or less V squared is equal to V0 squared plus 2a x minus x0. So it's pretty much what's going on here. We got a slightly different order, but that's okay. We need that slightly different order because the answer is going to come out under a square root, so it'd be a negative if it wasn't. So it's going to be the square root of 2 times 9.80 meters per second every second times 3.00 minus 1.00. And I'll just put meters over there. So when I actually do this calculation, I get the square root of, sorry, I had an extra symbol on my board. So 2 times 9.8 times parentheses 3 minus 1. That's 6.26. Actually, I'm gonna call this 2610, and that's more than enough sig figs, as you can see. So that's the final answer. 6.26 meters per second. Your book would, since they only use 3.0 and 1.0, they would have called that 6.3. And I just looked at their answer, and their answer was 6.3. I hinted to you that it didn't matter where we used the U to be 0. So now I'm going to show you alternative solution. So in this case, we're going to say U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. And this time I am going to say U is equal to 0. So there's where U equals 0 in the alternative. So when I go through and do this, I can now say, well, it's going to start with 0 kinetic energy because they're dropping it. There's not going to be work put into it. Now the final kinetic energy, or the final potential energy, is going to actually be 0 because where I defined it for this particular problem, and work out and E loss is going to be 0 as well. So all we have now is M times G times, now instead of Y1, I actually have to figure out how high above that spot is. So that's going to be 3.00 meters minus 1.00 meters. That's how high it actually is from the U equals 0 point, which is the whole issue that we're doing. Now all of that is equal to just 1/2 mv final squared. Again, you can see that the mass is irrelevant, which is exactly what Galileo taught us. And we can find out that V final is equal to the square root of 2 times 9.80 meters per second times 2.00 meters, which gives me again 6.2610 meters per second. So when you actually explicitly put it in, you can see exactly how it works. It just basically the math forces you to do a subtraction on the left-hand side that was done in reality from the right-hand side last time. So that's all it is. What really matters, as your book said, is the change in potential energy. Does anybody have any questions on that one? Okay. Another problem I like to do is a ballistic pendulum. So I'm going to do one of those. And I'll actually make sure you read over, like always, all the examples in the book from this chapter and the conceptual examples. They're really helpful. There's a really good one with a person sliding down a water flume, for instance. But anyways, that's a good question. What I want to do is I want to imagine a bullet flying in the sky. It's been fired and by some rifle or whatever, and it's moving with a velocity big V. So I might even put it like that so you can see that it really is a big V. When I do that, then I am going to allow it to run into a big, massive block of wood. Maybe like a 2x12 that's been, or excuse me, a 12x12 that's been cut down to maybe 1.5 feet long, right? So you've got basically, if it hits in the middle, it'll be 6 inches from the right side, 6 inches from the left side, 6 inches from the top, 6 inches from the bottom, and it'll have to go through an entire 2 foot of wood to come out the other side. So that's probably not going to happen. This is the initial scenario, and this guy right here has a height, or excuse me, has a mass big M, and this bullet has a mass little m. Now, in addition to that, this little, or I say little, this heavy block actually is attached to a sealant and is free to swing like a pendulum. So what's going to happen is after the bullet hits, then we're going to have basically this block with a bullet embedded inside of it, mushrooms and all sorts of good stuff like that, now having a mass of M plus big M and moving with a velocity V1. And because of that velocity V1, that's going to cause the swing like a pendulum. And ultimately what we're going to see is the block doing this number. This is just how high it was above where it started off at. So we still have the bullet in there, all beat up, mushroomed, and still have the mass M plus M. But what we want to know is what is the initial velocity V, the muzzle velocity. So this is a test, for instance, you could in principle use to determine the muzzle velocity of whatever gun you're firing. Of course, you got to be careful because bullets do bounce off of things sometimes, and sometimes they bounce like right straight back at you. So that could be a bit of a problem. So I'm not recommending you guys try any of this. I'm just saying this is a realistic and feasible way to go about figuring out what your muzzle velocity is. So what we're going to do with this one is we're going to use something that actually starts into the next chapter, which is conservation of momentum. So I like bringing this in early, but basically what happens in a collision is this bullet has a momentum, and momentum is defined to be mass times velocity. I would definitely encourage you guys to think, does that mass times velocity fit what we think of as our common use of the word momentum? Like, where do you normally in everyday life hear the word momentum? Anybody have an answer to that?
I mean, usually I think we use it as a context of a force. Like we need some oomph to give me something, you know, to overcome something, but that's not really what's said here. All momentum is just whatever the mass with the quantum, what that's the mass and the force of product. Right. It doesn't imply any kind of like oomph.
Right. So, but have you ever heard it say in sporting events? Have you ever heard the word momentum?
Yeah, I guess keep the
momentum going.
Keep scoring, keep doing as you're doing.
Right. And it's yeah, it often is like that. You got to keep your momentum. In other words, if you're on a roll, you want to stay on a roll, or you need to steal back the momentum because this team just came back from behind or something like that. Both of those imply yeah, it does imply a sort of motion, but it also implies a sluggishness, a resistance to change. And that's sort of it. It turns out the definition of momentum of a single body is just the mass of the body times its velocity. And you can see, of course, that means momentum is a vector quantity. And it turns out when you look at Newton's second law of motion, the way he actually wrote it, what you would use is the summation of the forces is actually equal to dp dt. That's what he really said. And you can see that in a special case, if m equals a constant, then you get summation of the forces is equal to m dv dt, which is the version I just used, right? So you see that's sort of a special case. But what we know about momentum is looking at this equation right here, the summation of the forces is equal to dp dt. If the net force acting on a body or a system is 0, so if the net force acting on a system, and I'm saying system because you don't always have to use just one body when you're talking about Newton's second law. Remember, I told you that is a way you could do the Atwood machine at treating both blocks and the string as one body, but it doesn't allow you to solve for the tension, and it also really begs you to make mistakes. So I'm just harking back to the fact that you can actually apply it to not just one mass, but a system of masses. So in this, if the net force acting on a system is 0, then dp dt is equal to 0. And what do you know about a function whose derivative is 0?
It's a constant.
It's a constant. So that means p equals a constant. In this case, is a constant vector, of course, but still a constant. So when we consider our system to be the little bullet with velocity v, big V that is, and the big mass, big M, if we consider that to be our system, then there is a force exchange, but the force is internal. It's the force of the bullet on the block when it starts to embed itself. But that's one part of the system acting on its own another part of the system. So because of that, that's not something that appears on the left-hand side of F equals ma or F equals dp dt. So this tells us that momentum will be conserved. Therefore, we initially have momentum. This is called momentum conservation. So momentum conservation. The way I can do that is I'm going to say P initial is equal to P final. That's the conservation of momentum equation. The initial momentum is just little m times big V. And I'm really just going in the X direction. So the fact that it being positive or negative is all the direction I need to make it a vector. So I'm just going to treat it like that. And then what I'm going to do is say, well, after the fact, the mass of the system is still the same. It's m plus m. But in this case, now they're both moving. So they both have momentum and they're moving at the same speed. And that same speed is what I called V1. So that tells us that V1 will in fact be equal to m over m plus big M times the big V velocity. Okay. I solved it for that for a reason, because now we're going to use conservation of energy methods to find out what that final velocity is. So let's do this. Let's say U initial plus K initial plus E loss, or excuse me, plus W out. I was writing the wrong side in my head. Plus W out is equal to U final plus K final plus W in or W out. I even wrote that on the wrong side, plus E loss. Good Lord, what am I doing? All right, so in this scenario, we're just going from the red frame, the red picture to the blue picture, okay? So what we know is it has initial potential energy equal to 0 because it's at the lowest point, and we're choosing to call the height of the bottom of that big block to be the position where what U equals 0. It does have a initial kinetic energy. There's not going to be any work put into the system. The final kinetic energy, potential energy is going to be something. We're going to work that out, and we're going to assume we actually know that. So what we're seeing with all these problems is that we know little m, we know big M, and we know H. Okay. So the final kinetic energy, of course, is going to be 0 because it's going to ride up or swing up until it gets to some max height. And we might put some kind of device in there to stop it at that height, or you might just film it and see how high it got and fine tune that by filming and then measuring the exact height. So any of that's fair game. All of this becomes 0. Ultimately, I get 1/2 of, oops, go back to blue, going back to that blue. 1/2 of parentheses M plus big M V1 squared is equal to M plus big M times G times H. So we can now plug in that V1 if we wanted to, and then we can solve for the big V. So that's what we're going to do. This is going to be 1/2 M plus big M times M squared over M plus big M squared. And all that's going to be times the big V squared. And all that's equal to M plus big M times G times H. You can see that, of course, one of these M plus M's is going to cancel out there. And now all we have is, I'm going to pull the 2 and the remaining M plus M to the right-hand side. So that'll give me lowercase m squared V squared is equal to 2 times M plus M. Notice I already had one there. Now I've got 2 of them there. So it's going to become squared times G times H. So now I can say, well, V is going to be 2 M plus big M squared times G times H over little m squared square root, which equals just M plus big M over little m times the square root of 2GH. So that's what the total velocity is, the muzzle velocity of the gun. That's what that is. Anybody have any questions on that? Right, as nicely as I wanted it to. So for instance, if you you could throw some numbers at this, you could say, oh, I just switched to the wrong one. Sorry. Okay, so for instance, let big M be equal to I want it to be about 50 pounds. So I'm going to say about 20 kilograms. Anybody know any masses of a bullet round? You can Google it real quick. Sometimes I almost always have somebody that's a Marine or still a avid gun fan or something along those lines, and sometimes I actually know that. So that's why I asked you guys. Let's look up. Let's say we're going to take an AR 15 bullet mass. It's 4 grams. So M is 4.0 grams. And let's say this big block lifted, let's say H is going to be about 5.00 centimeters. And I'm going to go ahead and pretend that's 4.00 grams. So we'll have 3 sig figs on everything. If this is the case, then I should be able to find the velocity of the bullet that would actually do that. And what I get is, let's see. So the 20 kilograms is going to be 20.004. 20.004 divided by 0.004 kilograms. And now I'm going to multiply that by the square root of 2 times 9.8 times 0.05. Close parentheses. And that gives me a really unbelievably high velocity of 4,951 meters per second. And this is a completely unrealistic answer, by the way. Typical AR-15 muzzle velocities is usually only order of 1,000 meters per second, not 5,000. So actually, yeah, I'm looking at it right now. The Armalite AR-15 223 caliber fires a 223 Remington, and its muzzle velocity is 3,300 feet per second, or 1,006 meters per second. So that is a very unrealistic thing, because the one, I used a really heavy 20 kilogram wood block. That's pretty darn heavy, and I had it lift up 5 centimeters. So that's a pretty big deal. Anybody have any questions on that one? Okay. All right. This is actually something nice. Let me stop sharing. I'm going to start sharing a different screen. Let me share this one. So here's the speeds over a water slide, is what I'm trying to show you. So I'm going to say share screen. I'm going to choose this one, that one. So this is a good conceptual problem that I want you to see, and it fits nicely with the conservation of energy, but it also makes you go outside of the equations and think about the reality of what's going on. So 2 water slides at a pool are shaped differently, but start at the same height. Lowercase h. 2 riders, Paul and Jeannie, start from rest at the same time on different slides. A, which rider, Paul or Jean, is traveling faster at the bottom, and B, which rider makes it to the bottom first. Ignore friction and assume both slides have the same path length. Okay, so they have supposedly the same path length. So what do you think? Anybody have any ideas of which one would be faster?
The straight down one would be faster.
Yeah, at least at that point on the straight down leg, you're definitely going to be going a lot faster than essentially any part that Jeannie and them Jeannie's riding. Well, maybe right here, this little part might be roughly as steep as that. But the thing is, notice this one starts off very gradually, so it's going almost zero, almost zero, almost zero, almost zero. Y'all do see the little pointer I'm holding up on the screen, right? I just realized I'm using a mouse pointer. I'm not sure y'all are even seeing that, but I think you are. So almost zero, almost zero, almost zero, whereas she's already gotten a decent speed by the time she gets to here. And because of that, what you know is at all times she's going to be going probably faster than him, because this part right here did allow her to get a pretty high speed. So she's actually going to be going faster at all points in time. And because of that, when you get to the very bottom, they're probably pretty close to having the same speed, because, you know, he had such a huge velocity at the end. And since they went the same distance, but this one was always going faster, obviously Jeannie's going to make it to the bottom first. So it says each rider's initial potential energy, mgh, gets transformed into kinetic energy. So the speed v at the bottom is obtained from 1/2 mv squared equals mgh. The mass cancels, so the speed will be the same regardless of the mass of the rider. Since they descend from the same vertical height, they will finish with the same speed. Note that Jeannie is consistently at a lower elevation than Paul at any instant until the end. This means she has converted her potential energy to kinetic energy earlier. Consequently, she is traveling faster than Paul at each moment during the trip, and so gets to the bottom first. Does that make sense to everyone? You know, it's cool because you actually did have to use that little, or one of the parts that I think is cool about it is you have to assume that the path length's the same, because if Jeannie had a hugely different path length, like much longer, the fact that she went faster might not be big enough. It might not be a large enough speed difference to make up for the longer path she traveled. So it's, like I said, it's a good conceptual problem. I like it. Roller coaster car speed using conservation of energy. That was a good example. Very straightforward. I think you can do that one, no problem. So we'll move on. Pole vault. Estimate the kinetic energy and the speed required for a 70 kilogram pole vaulter to just pass over a 5 meter high bar. Assume the vaulter center of mass is initially 0.90 meters off the ground and reaches its maximum height at the level of the bar itself. Okay, so that's kind of a neat problem. And I think, well, I think we can work it. Actually, let me just explain it here. So it says approach. We equate the total energy just before the vaulter places the end of the pole onto the ground, and the pole begins to bend and store potential energy. With the vaulter's total energy when passing over the bar, we ignore the small amount of kinetic energy at this point. We choose the initial position of the vaulter's center of mass to be y1 equals 0. The vaulter's center of mass must then be raised to a height of 5 minus 0.9. So notice they made the center of mass of the vaulter be the u equals 0 spot. That's why they had to subtract out that 0.9, which is the same thing I had to do when I made 1 meter up the 0 of potential. I had to take the 3 meters that the rock was up before and subtract from that 1 meter. So the same thing's going on here. So what they're saying is let's let all the kinetic energy be turned into all of the potential energy. So this is not unlike mine, except theirs only has U initial, K initial equals U final plus K final. But in this case, I would have came up with exactly the same thing, because I would have called work in 0, I would have called work out 0, and I would have called E loss 0. So you end up getting just 1/2 mv1 squared equals mgy2. That hopefully jogs your memory, as yet when you solve it, it's going to be another kinematic equation. In fact, the exact same one, the v squared equals v initial squared plus 2g x minus x0. So in this case, you actually had to be moving about 9 meters per second. 9 meters per second, if I remember correctly, is, divide that by 0.44. Yeah, it's about 20 miles per hour. They need to be going pretty fast. So yeah, that's not a trivial speed, of course. Toy dart gun's another good scenario. This is just something where you've got a mass pressed against a spring. So the dart has a mass of 0.100 kilograms. It's pressed against the spring of a toy dart gun. Let's show you the picture down here. So you can imagine you've all had either a gun like this, or you at least had maybe one of them little frogs or something that had a little suction cup on the bottom, and you squeezed it down. And when you did, it would stay locked in position. And then after some time, the suction cup would lose mass or it would lose its strength, and the spring would win and release the thing and it'd jump up in the air. That's the same sort of thing here. So you're using the spring to have a stored potential energy. So you could actually use this using my equation. You could actually start off with U initial plus K initial plus work in. You can either use this 1/2 kx squared as work in, or you could use it as potential energy, 1/2 kx squared, where x is the amount you compress the spring, which is 6 centimeters. So you could use it that way as well. But at the end, what you have to know is the right-hand side is going to be equal to, of course, U final, which is going to be 0 because the spring's completely released now, plus kinetic energy final, 1/2 mv squared, plus work out, which is 0, plus E loss, which is 0, because we're ignoring air resistance and all that good stuff. And when you do that, you turn out that this spring, which has a spring constant of 250 newtons per meter, 250, remember, a newton is about 1/4 of a pound. So if you divided that by 4, you get what, about 65 pounds. So you'd actually have to compress this spring a whole meter in distance to get 65 pounds. So you can tell this isn't a hugely strong spring, but it's good enough. So when you get the answer, it turns out to be 3 meters per second. Any questions on that? This example. Okay. Yeah, this is them basically just making the same argument that I did just now. You can treat 1/2 kx squared as a potential energy as well. So a ball of mass 2.60 kilograms starting from rest falls on the vertical distance of h equal 55 centimeters before striking a vertical cold spring, which compresses. So that's actually a neat little problem, because you're dropping a ball. It's losing potential energy as it falls because mgy, the y is getting smaller and smaller and smaller, and then all of a sudden it hits the spring and the y continues to get smaller, but now it's building up another kind of potential energy, 1/2 kx squared. So that's a good example for you to check. I'm not going to read any more of these examples for you, but I do want to work some problems. So let's look, for instance, at this one. I think this is pretty good. A simple pendulum shown in figure 814 consists of a small bob of mass m suspended by a massless cord of length L. The bob is released without a push at t equals 0, where the cord makes an angle of theta equals theta 0 to the vertical. A, describe the motion of the bob in terms of kinetic and potential energy, then determine the speed of the bob. B, as a function of position as it swings back and forth, and C, at the lowest point of the swing. D, find the tension in the cord, ignore air resistance and friction. Okay, so let's look at the diagram. And now I'm going to stop the share. Everybody sees the diagram real quick. So actually, I'll draw that before I stop sharing that particular screen. So let me draw that pendulum. Okay, so I'm drawing the length. Notice they were kind enough to let you in on a little secret here. They're letting you know on this diagram that the distance from the ceiling to the center of the bob at the bottom is the length of the cord, what we call L. And we're going to assume that let it go at theta 0, and then they want to know the things such as, let me write those down real quick. A, they want to know, describe the motion. They want to describe the motion in terms of kinetic and potential energy. B, they want us to determine the speed v as a function of theta. And C, the speed at the bottom. B at the bottom equals question mark. D, they want to know the tension of the cord. D, tension. Okay, so now we've got all that. I can stop sharing this way, and I can start sharing this other way. Share my document cam, or my document reader thingy. My iPad, that's what it is. Ooh. Anybody have any questions before we go on? Okay, now take it a second to get it there. So now I've gotten everything written down. I've got the diagram drawn, all that stuff. I need to work out the details of it, of course. And I need to think not only about the initial position, which is what I chose to draw. I need to think about it at any arbitrary position theta as well. So I'm going to draw over here and just sort of plot out the path this thing is going to go in. And it's probably going to go, it should go back to the same height that it initially was. So if I consider this particular spot right here and call this angle theta, then I realize that this length, of course, is L, and that's from here all the way to there. And then this is the H that has occurred as a result of the angle being theta, is that little distance right there. And this distance right here, of course, is L as well. This distance from the ceiling down to the bottom is L as well. So what we need to do is we need to take L and subtract this little bit from it. That little bit is L cosine theta. So L cosine theta is this length. And that means the height as a function of theta is actually going to be L minus L cosine theta in general. Does everybody see how I got L minus L cosine theta for the height? No questions on that? All right. So we'll keep on. That's what the height is. And now we're going to use our conservation of energy scenario. So we've got U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. They told us to basically ignore all the air resistance and frictions and stuff like that. We obviously don't really have any works going in. The person didn't give it a push or anything like that. But we can say the initial potential energy was basically M times G times parenthesis L minus L cosine theta 0. And what we have then is M being the mass here times G times L times 1 minus cosine theta. 0. So that's me just plugging in H for theta 0. That's the initial potential energy. At any time later, it's going to have a potential energy mg L times 1 minus cosine theta. And it's going to have a kinetic energy equal to 1/2 m v sub theta squared, where again that v has some relationship to the actual angle. Any questions on that?
Professor, wouldn't the one on the left just be MGL and the one on the right be that 1 minus cosine theta?
No, the reason being is you're sort of looking at how far it's hanging down, and I'm trying to focus on how high above its lowest point it is. So the L is the lowest distance it'll be from the, or the highest distance it'll be from the ceiling, but it does get smaller than that by amount L cosine theta, or in this case L cosine theta 0. You see that? You can do like this, for instance. That's the L cosine theta right there. And then this is the H of theta 0. Do you see now why you have to have the L minus L cosine theta?
It won't matter, I guess, because the angle is 90, I guess. So, well, angle's 90 equals 0. Yeah, so it comes MGL on the left side when it's 90 degrees, I guess.
You get a, yeah, you would get a height of L then. Which is, yeah, that's consistent with what you want, right? All right. So we can go ahead and move with this. What we can do is we can have all of this in terms of just V theta. For instance, I'm going to divide through by the mass. And that gives me, I don't want to keep switching colors like this. That gives me GL times 1 minus cosine theta 0. I'm also going to pull the other one over here, it'd be minus GL times 1 minus cosine theta for any angle theta. And then all that's equal to 1/2 V at theta squared. So I can multiply through by G, and now I can, or excuse me, multiply through by 2. So it'll be 2GL times, now I'm going to distribute. I'll have a 1 minus cosine theta 0 minus 1 plus cosine theta. That's basically combining all those like terms in there. That's all equal to V theta squared. The 1 and the negative 1 cancel each other out, and I get V at theta is equal to the square root of 2GL times cosine theta 0 minus cosine theta. So what the description part, which we sort of skipped, what they're wanting you to realize is that this is basically just a Ziploc bag. Half of the Ziploc bag is the vat or baffle or whatever that I called it, representing kinetic energy, and half is potential energy. When somewhere in between theta 0 and theta equals 0, the plumb bob on the pendulum will actually have the same kinetic energy as it does potential energy at one point in time. At that point, both both baffles in the Ziploc bag are equally full. Of course, then it's going to continue moving until the kinetic energy part gets smaller and smaller and smaller as it reaches its max height on the other side, which can't be any higher than theta 0. And then it's going to come back and start to decrease the potential energy, which means when it gets to the bottom, the kinetic energy is going to reach a maximum, and so on and so forth. So that's sort of the motion they're talking about. This is part B, the velocity as a function of theta. And now for part C, I have to write that in red. For part C, we want to figure out when theta equals 0. Because when theta equals 0, that means it's at the bottom. So that gives us V bottom is equal to the square root of 2GL times cosine theta 0 minus cosine of 0 degrees, of course, is 1. So that should be the formula there. And trying to see if I got everything right. Yeah, I got that right. Oh, wait a second. Did everybody? I've actually got my thetas in the wrong order. That's what I was just noticing. I wrote them down, not paying any attention. Notice when I did this part right here, I got 1 minus cosine theta 0 minus 1 plus cosine theta. So it should be cosine theta minus cosine theta 0. I put the subscript on the wrong one. I don't know if I don't know why I did this, but that way. Now over here, I'm going to put the 0 on that one. So now when I do this, this should not be that. It should be it should be 1. Whoa, no. It should be 1 minus cosine theta 0. So that's the velocity at the bottom is 1 minus cosine theta 0. What they're ultimately wanting us to do is figure out the tension in the rope. Specifically, they want the tension in the rope as a function of theta. So now we're going to do that. Anybody have any questions on this part C? Or yeah, part C. Okay, so this is probably in some sense this is like the most important part of the problem, not because you're learning something grandiose, but it's a good reminder that hey, we're doing conservation of energy, but all the things that we learned are still in play and still have to be used. So once we got out of kinematics, for instance, you still need to know kinematics, and for instance, you can use that to compare to the equations you get for velocity from conservation of energy. Not only that, you can use those equations if you find the final velocity. You could use it to find out if the acceleration is actually a constant, and you could actually apply it to Newton's laws of motion and find out things there too. So in this case, what we're going to see is we actually are going to have the pendulum bob has to actually accelerate at mv squared over L, where L is the radius of the turn, or the length of the pendulum. So with that in mind, we need to be able to find out what the tension is. So if we take a free body diagram, let's say like this, There's your mass M. There's your force of tension. I normally just call that a T, but your book called it FT, so I chose to do it that way. We also have acting here a mass, a gravitational pull M times G. That's all well and good. You can actually set up a coordinate system. And in the coordinate system, this is one where something's tilted, but you definitely still want to use the normal coordinate system. I'm going to say, yeah, I think this will be good. No, this will not be good. Let's try this way. I'm going to say, I'm going to say this is my y-axis. And this is my x-axis. And then when I do that, I can break up my mg into components. If this is the angle theta, then this too is the angle theta, and this is mg cosine theta. And this one is mg sine theta. Okay. The main thing is this thing has to be accelerated, and it has to be accelerated at mv squared over L. So Newton's second law gives me at least for the acceleration in the y direction, it gives me ft minus mg cosine theta is equal to mv squared over L. That means the force due to tension, I can just solve for that. The force due to the tension in the rope is just mg cosine theta plus m over L times 2gl times 1 minus, or excuse me, times cosine minus cosine theta minus cosine theta 0, like that. So basically I just took the velocity from part B and just put it in there and squared it. Of course, the square made the square root go away. And now I can see also that the L is going to cancel out with the L. And basically we're going to get that the tension FT is going to be just M times G times cosine theta plus 2 cosine theta minus cosine theta 0, or ultimately we're going to have 3 cosine theta. Yeah, 3 cosine theta minus cosine theta 0. So make sure, oh yeah, there's supposed to be a 2 there too. Oops, everybody left off that 2. I distributed everything but the 2. Let's fix that real quick. And that's the answer. So anybody have any questions on that? Notice I did write this expression as a dimensionless quantity, the 3 cosine theta minus 2 cosine theta 0, and a quantity mg that is obviously the right units for the thing on the left, i.e. it has units of force. So that's why it's written that way. That's a good way to try to solve your problems every time. Anybody have any questions about that procedure, about any of the steps I took, anything like that?
Yeah, the potential energy of the beginning. Not understanding the first on the left side, your initial
You talk
potential
about
energy.
up here.
Yes.
Okay. So what we know is the red part that I've drawn above on that little vertical red line that I've drawn. That is the L cosine theta. That's what L cosine theta looks like. Once you realize that and you say, consider the angle being 0, then you'd see the mass would be right here. If the angle is 0, you see that dot?
Yes.
So that's theta equals 0. So if we choose to use that particular height as the 0 of potential energy, then the distance between that and the end of that red line is the height. Hence, I've got it drawn there. I've got it drawn for the blue line, but in the case of theta equals 0, or theta, when you're comparing it to theta 0, you can see that h goes all the way from that little black dot up to the end of that red line. Well, that quantity is from the top of the red line all the way to the black dot is the length L. And that little bit right there is the length L minus L cosine theta. So that's why we can write mg times L minus L cosine theta. Does that help you?
I just don't understand why you took the. Are you only trying to find the where H is at?
Yes. Ideally, I would like to just be able to write mgh on the left-hand side, because that's, we're starting at mgh, where h is some arbitrary height that corresponds to the pendulum being slipped back at that theta 0 angle. So the L times parenthesis 1 minus cosine theta 0 is the h.
Okay.
And that's part that you might not be missing. That's the general opening of the problem, is you lift the pendulum back holding the string taut until you reach some initial angle, which we call theta 0. As long as you drop it from there, you're not going to ever go even as high as that, much less higher. So you start that, and that's the total energy it has in it, is basically that potential energy.
Okay.
Right. Okay, so that was another good problem. Let's go ahead and it's 11:30. Let's give you guys a 10-minute break and be back at 11:40. I'm here in case you want to ask me questions right now, even though we're quote unquote taking a break. But feel free to ask me any questions. I am here.
Can you check your chat?
Gotcha. I was wondering, somebody wrote in physics class earlier, I was wondering what it was. Now see, we can see, okay. In part C, theta 0 and theta. Okay. No, I mean, they can be. There can be a special instance where theta is equal to theta 0. If we ignore air resistance, what will happen is the instant you let go of the pendulum, it will swing through that angle theta 0, reaching 0. And then it will go back up to the exact same height if there is 0 air resistance and friction. And to be honest with you, it's going to come so close the first time that even if it wasn't, if there was considerable air resistance or something like that, it's still probably too small to measure that it didn't quite make it to the same height. So really, at that point, it will be. But what I was trying to do is choose an arbitrary theta and just related the original energy to that. So my idea was I'm going to have a pendulum, and I'm going to say the left-hand side is the instant, the left-hand side of the energy equation, UI plus KI plus work in equals blah, blah, blah. That left-hand side is going to be the initial condition where the person has pulled the pendulum bob up and angle theta 0. So with that in mind, you're going to release it there. That's going to have 0 kinetic energy. You're not putting any work into it. You did technically, you actually put work into it to get it up to the height of mg time, or excuse me, height of L times 1 minus cosine theta 0, that is. So that's what the left-hand side is. And then I just said at any theta later, I'm going to have a 1/2 mv of theta squared. That's the kinetic energy. But I'm also going to have a corresponding mg L parentheses 1 minus cosine of the arbitrary angle theta, because always the height is going to be given by L minus L cosine theta for whatever theta you use. Hopefully that helped, and really hopefully that I didn't make it worse.
So, sir, I know you said that you award partial credit for work and everything like that submitted. And I sent you an email as well.
Okay.
One of my problems on the test, I had the wrong damn sign at the end of it.
Gotcha.
And I noticed it afterwards. But regardless, when will we see, if at all, our grade to be updated? Will it be sometime next week or something like that?
Oh no, I hope as far as your test goes, that should be done not Wednesday. It should probably be done by Friday.
Okay.
Yeah.
Cool.
I'm not that quick getting my lab reports back, partly because my students don't always turn them in on time, and I hate taking points off for just being late. So a lot of times I just wait until all of them are in and I'll start grading them. I shouldn't do that. It actually harms the students that are doing the right thing, and it helps the students that are doing the wrong thing. But anyways, that's normally why I'm slow on that. And with tests, I always try to get that over with really quickly. Final exams, that sort of thing. I try to get you to know the grade immediately.
All right.
Generally, they won't go up. There will be a few cases where they might go up, but generally speaking, they're more likely to go down, if anything, just because students will not know how to do one of the problems or that I need to show the work on. But we'll see.
Understood.
I
Thank
get
you.
you Friday.
All right.
You're welcome.
Professor, have you opened the lab that we're supposed to do or put it on the site, Canvas site yet?
No, in fact, I was still working on getting the document. Let me actually check that while I was here. I thought I had uploaded it already, but just before I logged in and realized I hadn't made my Zoom appointment, I realized that I didn't have that up there. So I'm trying to find it, see if I've even got it on here. Otherwise, I have to get it from somewhere else. I think it's here. Let's see. Let me see. Intro to lab. Did we ever do the introduction to error propagation lab? I've got it listed in week 1 like we did it, but I could have sworn we didn't do it. And I don't see where it's been turned in.
I don't remember it.
Let me pull it open real quick while we're looking here. Yeah, that's what I want. So I'm talking about this thing right here. Well, that wasn't supposed to be the video. Oh, that's cool. Yeah, I was trying to look at something else and went to the actual video. Go back here. Maybe I just put that there specifically so y'all would have access to it, but unit conversion of here. Yeah, it looks like I definitely didn't do it because I did the intro to lab. I did the spreadsheet review. Actually, I wouldn't have done a spreadsheet review with you guys. Actually, we did do that early. That's what it was. Oh, these are just links. Okay, so yeah, I don't think I did that. Then you're graphing one, then you're graphing two, then you're graphing one. Then you're graphing two. Wonder if I have it in here. Not here either, eh? If your digit rules are there, that's helpful, but not what I wanted. All right. So it's definitely not there. So I'm pretty confident that what I had planned on doing, we haven't done. I did need to make sure of that. There's the document. Excellent. I'm going to put it up now. Good. Week 7 I just created. File. Hey, y'all now should be able to see a week 7.
Mr. Younger, could I ask you a question?
Yes.
I've emailed you a handful of times. We talked about it in class on Wednesday, I believe, but
Yes.
all the chapter practices
Oh,
from
yeah, that's
like
right.
5 and after are still closed.
Thank you. I appreciate that.
Yes, sir.
Yeah, I remember you talking to me, and I remember thinking, "Oh, I'll do that as soon as I get home," and I didn't do it anyway. Okay. Oh, I see. So yeah, they had like a weird date or something. May 9th. Which chapter were you able to do? Any of them, or were all of them?
We can access 1 through 4, but then 5 and the rest of them are all
Okay.
locked.
Thanks. I needed that piece of information. Okay, yeah, I see. Not supposed to have been toolboxes there at all. I don't even know why I filled that in. Let's do save on that one. Oh, chapter 5 is now fixed. Chapters 6. Yeah, it has an until date too. 6 is now available. I'm glad you did this now. So much easier when I just do it in real time because I know I'll always forget it if I don't. So 7 is now available. Let's do 8, 9. Well, I don't see 8, so that means that's somewhere weird. I figure out where that. Oh, there it is. Chapter 8 should be available now. Chapter 9 is coming. Oh, good news. Chapter 9 was already open. So yay for us. Hopefully 10 is too. Let's see. It looks like the rest are good to go. 10, 11, 14, 15, and 36. All right, good deal. Anybody have any questions before we get back into it? All right, so I've basically done all the different topics of this chapter that were on chapter 8. So I'm going to go on into chapter 9. I'm going to start off by sharing with you the chapter 9 pictures, basically. So let's do this, share screen. That one. Okay, so we're going to learn yet another tool, which I've already hinted at a couple times, and is especially today, I even used it to solve that projectile motion problem with basically or not projectile motion, but the ballistic pendulum problem. But it's conservation of momentum, and it's specifically what we call linear momentum. It turns out to be another momentum that we call angular momentum, which probably most of you have already heard of before, but the deal is once we start learning about rotational motion, then we can combine what we've learned about linear motion with what we know about rotational motion. And those two pieces put together allows us to fully understand motion. So for instance, if I throw a BB or a marble or something like that, it doesn't matter very much whether the BB or the marble is spinning left, spinning right. Of course, it makes some difference in terms of the curving that it would do or something like that in terms of fluid mechanics. And in some sense, we would touch on that if we did cover the chapter on fluid mechanics, but we never do that in this course. So that's neither here nor there. But imagine throwing, instead of something that is insignificantly different because of spinning or whatever, something major like a hammer. If you throw a hammer, that's a whole different problem. You've got basically a hammer or an axe that you're throwing has a center of mass. That center of mass is what's going to obey or is going to behave like a projectile so that it actually follows the path of a parabola. But the rest of the parts of it are going to do very weird things. In fact, they're going to spiral around that center of mass and stuff like that. So how do we actually do that? Well, it turns out all you have to do is solve the center of mass problem of it as if it's a point particle. And then if you want to know where the head is at any point in time, you're going to treat the hammer or axe as if it's a body that's not a point mass. And that body is actually rotating about the center of mass, and you can figure out what the rotation rate is, or you can, assign it a rotation rate and figure out at any point in time whether the head is up or the head is down, whether it's facing forward, facing backwards, which is really, ultimately what you want to do if you want to really be someone who uses, for instance, an axe as a safety instrument or for hunting or something like that. Then obviously you don't want to throw your axe and have it hit someone or hit a bear with just the butt end of the axe. You obviously want the pointy end to hurt. So that's all that's needed in terms of physics to solve such problems. But before we do that, we have to first talk about linear momentum. And this is really good because it's this tool that allows us to solve problems regarding collisions. Usually, for instance, when two cars collide, the biggest forces are forces that happen between the two cars. And if you treat the two cars as your system, those forces don't matter. All that really matters is the forces that the earth is applying to the car, whether it be through friction between the tires and the road or holding it up against gravity, that kind of stuff. All those forces are pretty tame and easy to deal with. So you can use conservation of linear momentum issues to work out collisions. And that's mostly what we do here in this chapter. So it says learning objectives relate an angle to the arc length on a circle of a particular radius. That's just S equals R times theta, and I don't know why they're putting that there. In fact, this all looks like they've got the learning objectives for the wrong chapter. No, they're doing okay for here. But 9-1, 9-2, and 9-3, and 9-4. 9-5 as well. Wow, all of this looks like, I mean, there's some of it that helps. The center of mass is an important thing, but yeah, that's weird. I think that's just a really bad series of typos. So here's your contents. These are really the learning objectives of momentum, and its relation to force. Section 2 is conservation of momentum. Section 3 is collision and impulse. Conservation of energy and momentum in collisions, elastic collisions, so on and so forth. Always answer these questions, and it's really irrelevant whether your answer is right or wrong. But the whole act of taking the time to read the question and answer it helps the learning process. So always do that. I'm never going to cover those in class specifically because I want you to do them. And if I cover them in class, there's going to be someone that hadn't already considered it, and that you just sort of ruined the learning opportunity for them. So anyways, make sure you do that. Chapter 9, we're starting with, as I said, it's momentum. There's your momentum. It's defined as momentum equals mass times velocity. And I've told you already that Newton's second law was really stated as the net force is equal to the instantaneous rate of change of momentum, and specifically linear momentum. When we start studying rotational motion, we'll find out there's an equivalent equation to Newton's second law. That one says instead of the summation of the forces is equal to mass times acceleration, or the summation of forces is equal to dp dt. Those are the two versions that we've worked with. We'll have the summation of the torques is equal to I times alpha, which is like the MA. But we also have the summation of the torques is equal to dl dt, like dp dt, where L is the angular momentum. So all of the stuff we're learning, we're going to find out has an exact analog in rotational motion. So what is the momentum? Well, it's really, like I said, it's just mass times velocity. If you're wanting to treat a system as opposed to a single object, then it's not only mass times velocity, it's mass times velocity for each little part. So if you're talking about, a piece of cheese, then you could literally take each little coordinate on the slice of cheese and imagine that's infinitesimally small. And then you have the little mass times the little velocity for that particular part of the cheese. Then you go adjacent to that little part and discretize it if you want. In other words, imagining it being in 1 micrometer by 1 micrometer by the thickness of the cheese. Make that your little cubic solid, and you say m times v for that. Then you go to the next one, is m times v for that, and then the next one m times v for that. And each of those are vector quantities, and you can do that. Or you could do it with separate pieces. Not unlike the Atwood machine where we had a pulley, a rope, and a mass and a mass. Those sort of could in principle be treated by F equals ma as a system, but we chose to treat it as F equals ma for one of them, F equals ma for the other one. But any of those times you do that, you can always just take the sum of all the masses and velocities, and that will be the total momentum of the system. If you have, for instance, 2 cars getting ready to collide, you could have this car moving with a mass times velocity, this car moving with a mass times velocity, and then you just add those 2 mass times velocities. That's the momentum of the system before the collision. And then after the collision, if momentum is conserved, that should be the same value. So you'd have m1 v1 final plus m2 v2 final for that. Again, vector quantities. So that's the way we can do it. A lot of times you're just going to be choosing one object, but sometimes you'll actually choose multiple objects, and sometimes that allows you to solve problems that you couldn't solve unless you treated it as 2 objects. Other parts you can't solve unless you treat it as one big object. So it's just a matter of you getting the experience to do that. So your book is going through the same part that I did, which is, for instance, taking F equals MA and showing you that it's really supposed to be F equals dP/dt. And then when you realize P is M times V, then dP/dt becomes D by dt of MV. And if M is a constant, you can pull that out in front and you get MA. So let's start off with a example. And the example we're going to start off with, this is again, chapter 9. I know you're not looking at my page yet, but I'll put it up in a second. Okay, so let's share my screen. Feel free to ask me questions at any time. You don't have to, wait for permission or anything like that. Raise your hand or any of that kind of stuff. Hey, there's no way it's not doing it. I'll try it again. Now it's showing. That's taking a moment. Okay, so this is what we're dealing with, the F equals dP/dt. This is, like I said, Newton's second law of motion. There's Newton's second law. Again, in a special case, then you get that. But again, that's in a special case. So just to get you started off, it says there's an example. It says a top tennis player, for a top tennis player, a tennis ball may leave the racket on the serve at a speed of 55 meters per second, about 120 miles per hour. If the ball has a mass of 0.060 kilograms and is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough? Excuse me, to lift a 70-kilogram person? So that's a neat little question, and that's the first thing we're going to try to solve here. So V is equal to 55 meters per second, which is about 120 miles per hour. This, even though he just came out with his new version of the text, this is actually pretty antiquated. Virtually all the women on the pro circuit are hitting at 120 miles per hour, and the elite female athletes, even the ones near retirement, like Venus and Serena Williams, are hitting in 135, 140 miles per hour. So it's a little dated for this period of time, but anyways, good enough. What they want to do is find, since the mass of the ball is equal to 0.060 kilograms, they would like to find what force is actually being applied to this. They're saying this is going to be 4 times 10 to the -3 seconds is how long it's in contact with it. And what they want to know is F is equal to question mark. So from Newton's second law, we'll have solution. Newton's second law, we have the summation of forces is equal to dP dt, which means the summation of forces is approximately equal to delta P over delta T. Well, delta P is P final minus P initial. So we can do this. We can say the summation of the forces, or the total force, is equal to P final, which is going to be 0.060 kilograms, times V final, which is 55 meters per second, minus 0, because it was going 0. Actually, you know from tennis, they actually toss it upwards, but you try not to let it have too much velocity in the direction that the serve is supposed to go, because then you'll have to lean out and hit the ball off balance, and you don't get as much a hit. You end up hitting it way high or down at the bottom of the net. So now we're going to divide all that by 4 times 10 to the negative third seconds. And what I get is 0.060 times 55 divided by 4 e to the negative 3. And that gives me 825 newtons. The weight of a 70 kilogram person is equal to 70 kilograms times 9.80 meters per second every second. And that's 686 newtons. So yes, you can lift a 140-pound person, which actually is even more than a 140-pound person. It's more like a 150-pound person with the force that's used in hitting the serve. Any questions on how that one was done? Pretty straightforward, right? That was example 9-1. Looks like we don't have any questions. Let me go into example 9-2. So 9-2, it says water leaves a hose at a rate of 1.5 kilograms per second. So I'm going to call that delta M over delta T is equal to 1.5 kilograms per second, with a speed V equal to 20 meters per second, and is aimed at the side of a car which stops it. What is the force exerted by the water on the car? Okay, so what you're imagining is basically little particles moving at velocity V, and they're actually going to hit the side of the car. So F, here's our solution. The summation of forces is equal to delta P over delta T. In this case, we could say it is going to be just V times delta M over delta T. So we'll take the velocity, which is 20 meters per second, and we will multiply that times the change in mass per time, which is 1.5 kilograms per second. Second disappeared. And that should do it. When we actually do this, we get 1.5 times 20 is actually 30. And notice the units come out to kilograms meters per second squared, which is in fact a Newton. Any questions on that? All right, so and this is really, I mean, a way to calculate what the force of a pressure washer, for instance, has. You can literally use the continuity equation, which says the density times the volume, or times the Yeah, density times the velocity is equal to the density times velocity. You can even understand, for instance, when water comes out of a faucet, the column of water narrows as it gets further and further down. That's again conservation of mass. So what's going on is because the density times the velocity maintains a constant amount, then when it's initially coming out, it's going very slowly. So it's the same amount of mass then as later, but later on the velocity is going to be much higher. So it's got to account for it by shrinking the actual cross-sectional area of the tube. So there's a lot of neat ways you can analyze water, either by treating it as if it's a string of little particles or just treating it as one big blob. And like ice cream coming out of an ice cream machine at McDonald's. Well, not at McDonald's because they're just never working, but in general, maybe at Wendy's. Okay. So one of the things, for instance, you can do if you imagine ice cream coming out like this, it's actually going to make a certain volume. The length implies that the volume that went out is actually the area times the length. In other words, this being the area right here. So if that's coming out of the pipe, then you know that's the particular volume coming out in a certain amount of time. So you can actually say, okay, well, I get a area times length over time coming in, let's say in the other side of the machine, and then leaving out this. Then this tells you that the continuity equation says A V A1 V1 equals A2 V2. So that's just another way we can think about water. Sometimes instead of having to worry about it being individual particles, you can think of it as sort of a fluid, and you think about area times velocity equals area times velocity, and that's called the continuity equation. And as long as you're using a liquid or molten solid or something like that, it works fine. When you get into using it for gases, though, gases are compressible, so you can't use that anymore. You actually have to use density times area times volume. That way you're conserving matter and not just volume. All right. So if you want to work on collisions, it turns out there's these really nice equations that your book derives for you. And I want to give you those now so you can get started on everything. And then we're going to take a quick break and go into the coverage for the lab. I just wanted to be able to get you started. If you look at example, for instance, example, oh, I must have missed it. Yeah, I did. Example 9.3, that's one of the classic easy momentum problems that get you started with collisions. But it turns out if you allow collisions to be along one dimension, you can actually get these really nice equations. And these really nice equations to me look a lot like the equations from the Atwood machine. So I want to give you those because you can solve so much with just these little equations. So and you can, if you want to see it derived, you can look on my YouTube channel, and you'll, just do a search on my YouTube channel for momentum, and you'll see that for a 1D head-on elastic collision, so one-dimensional, for that, we have, you could imagine, for instance, a object A which has a mass A, and object B, which has a mass MB. You can imagine them going to have a collision. Let's say this one has an initial velocity of v sub A, and this one has initial velocity of v sub B. And then after the collision, we now have A with a velocity VA prime and B with a velocity VB prime. So that's our setup. I haven't explained to you what elastic is, but I will in a second. When you do that, though, and you work with the elastic conditions as well as conservation of momentum, it's pretty straightforward to show that the VA minus VB, the difference in the velocities, just changes order. So becomes VA prime minus VB prime. So notice it's the VA minus VB before the collision is just different by a negative sign after the collision. Now, elastic. An elastic collision is a collision in which kinetic energy is conserved. In practice, that's only really a true scenario at the microscopic level, but you can get pretty close to it. And oddly enough, it's two rubber balls running into each other, two soft rubber balls, is quite a bit further away from being elastic than two steel balls running into each other. So pool balls and cue balls and stuff like that, those are much closer to elastic collisions. But you can imagine just the fact that you hear when two pool balls run into each other, that means some of the energy's been lost, because you can't have sound waves propagating from a collision without using any energy. You actually have to create the waves. So that alone tells you it's not exactly elastic collision, but as close as you can get to it and minimize things like that, sound and deformation of the body. For instance, that's the difference between a springy ball and a steel ball. A steel ball is not going to spring very much. It's not going to deform, because when you do deform the shapes of the ball, that actually is using up some energy. In fact, if you took a piece of aluminum and you just bent it back and forth over and over and over and over and over again, it would eventually get really warm. So what's happening there is that relative motion clearly takes and heats up the actual body. So it's clear that whenever a body deforms, it's going to use up a little bit of the energy. So that would not be an elastic collision. So the part of this derivation that gets you this is, first off, you start off with the conservation of momentum. Again, I'm not going to derive it for you. I just want you to know where it came from and stuff that you need to be able to do right now. So conservation of momentum. Can anybody remember? We just went over this a second ago. Can anybody remember under what conditions momentum is conserved?
Gonna guess conservative when a conservative force applies. I don't.
No, well, a lot of times if you have a conservative force, yes, that would be it. But in this case, it's kind of weird. But it came from Newton's second law. Newton's second law, remember, said dp dt, and then on the other side it said the summation of the forces. And conservation of momentum just means the momentum is a constant, and of course dp dt is a constant, is zero when the total force is zero. So conservation of momentum occurs when the total force on, well, total force on the system is 0. Of course, also really close to 0 is kind of helpful. You can sort of do that. But yeah, that's when conservation, that's when momentum is conserved, is when the summation of the forces, which equals dp dt, is equal to 0. Summation forces equals 0 implies dp dt equals 0, which implies p equals a constant. So that's when it occurs. So with this one, what we're talking about is we're going to say MA times VA plus MB times VB is equal to, notice that's the mass times velocity for object A and for object B before the collision. And then after the collision, that's got to be equal to MA VA prime plus MB VB prime. And that's for the final. Now, reducing it to one dimension makes life a little easier because you really just have the symbol VA being in the X direction. So you can even drop the vector symbols. You get MA VA plus MB VB is equal to MA VA prime plus MB VB prime. That's conservation of momentum. Okay. Now, conservation of kinetic energy. In this case, it's 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. So that's your conservation of kinetic energy. Any questions on that? All right, when we get back in the classroom, I will solve more problems of this variety. I just wanted you to have those equations so that you can start working on the chapter 9 homeworks. I should probably, while I'm here, I should probably go ahead and check the due dates on the assignments. Let's look at that real quick. I'm gonna check chapter 9. We're gonna go ahead and let's take a 10-minute break. And when you come back, I'm going to do a quick intro to what we're doing for lab, and then you guys can do the rest of it on your own. So go ahead and take a 10-minute break. Be back at, actually, let's make it a 15-minute break. Be back at 12:30. And I'm going to pause this video, and I would appreciate if someone could help me remember to unpause it when I get back. Anybody helps out with that? So we have a question that's been put into the chat notes. So let me address that real quick. So it says a elevator cable breaks when a 975 kilogram elevator is 22.5 meters above the top of a huge spring. So what we have here is what I'll call H equals 22.5. I know you're not seeing my tablet right yet. I want to write it down and then give it to you. That's 22.5 meters above a large spring. So let's say our spring is like that. Okay. And here's our elevator, which has a mass of 975 kilograms. And what they want to find out is delta x equals question mark. Okay, so we've got everything sort of written out there. This is a chapter 8 question, right?
This is chapter 7.
Chapter 7. Okay, the reason why I was asking is they would want you to use conservation of energy methods if it was in chapter 8, but since it's in chapter 7, we know chapter 7 is before the energy methods. In fact, all we had then was work. Well, actually, I guess chapter 7 was work and energy, so that it had that. It just didn't have the whole conservation law thing. So, yeah, okay. Yes. Okay. So we can work this using conservation of energy methods if we want. We can work this using force methods. The main thing that's going to happen is we know this object is going to fall, and the object will then fall with a height of 22.5 meters of fall. And then as it gets to the bottom of that 22.5 meters, it'll reach some max speed. And then at that point, it's going to be inhibited by the force of the spring, and the spring is going to bring it to a stop. And what we need to figure out is how much the spring will compress in doing so. So what you have is something where you can say the potential energy is 0 at the bottom of the compression. Now, you might think, since the spring is so large, that it's going to be a very small spring distance that's going to be done or compressed, but we don't know that necessarily. So it's really best to take into account the height above that minimal position and call that U equals 0 instead of calling this U equals 0. So then we could use my typical version, which is U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. What I'm
Are you
going
going to share your screen?
Oh yeah, thank you. Now I had remembered before, but this time I've forgotten again. So yeah, here we go. It should come up in a second. It just takes a little while. Waiting. It's trying to do it. Yes, we got it. Okay. So here's what I have. I've drawn the delta X is the amount of the spring compression, and I put U equals 0 at the bottom of that. So that makes it a little more complicated, but we can still work it. So I'm going to say the initial potential energy is the mass times G times H plus delta X. Because again, as I said, it's going to have a 0 of potential at what I consider the bottom of the motion, which would be when the spring is fully compressed as much as it's going to be compressed. The initial kinetic energy is 0. The work in is 0. The final potential energy, because I did that, is 0. And the final kinetic energy is 0 as well, because I'm examining it at the instant it comes to a stop at the bottom. I am going to just say this is work out, and that's equal to, that's equal to 1/2 K delta X squared, where delta X obviously is the compression of the spring. So what we have is mgh plus mg delta X plus or equals 1/2 K delta X squared. So I can say 1/2 K delta X squared minus mg delta X minus mgh is equal to 0. And you see that's a quadratic equation. I'm going to say delta X is equal to positive mg. Remember, it's negative b plus or minus the square root of b squared minus 4ac. So the b is the mg, and it's actually a negative, so I had to make it a negative of the negative as a positive, plus or minus the square root of b squared, that's m squared g squared, minus 4 times a, which is 1/2 K, times c, which is negative mgh. So b squared minus 4ac over 2a, and 2a is 2 times 1/2 K. So I can get mg plus or minus the square root of m squared g squared plus 2 mg k h. All of that over just plain k. So that should give it to me. Let's plug in the numbers. I'm going to say delta X is equal to 975 kilograms times 9.80 meters per second every second, plus or minus the square root of 975 kilograms times 9.80 meters per second squared plus 2 times 975 kilograms times 9.80 meters per second times K, which was 250. Actually, I need to see my chat. That's where it went. Oh yeah, K was 6.5 times 10 to the 4th. And then times H, which would be 22.5 meters. And I put all those units on there so we can check that it is, in fact, coming out with the right units. And this is 6.5 times 10 to the negative 10 to the 4th newtons per meter again. Okay, so let's work this out. The 975 times 9.8. That's 9,555. Plus or minus, and that's actually got one extra sig fig there, plus or minus the square root. Let's say 955. I'm going to square that. Plus 2 times 975 times 9.8 times 6.5 e to the 4th times 22.5. So under the square root, I get 2.8040. 2.8040 times 10 to the 10th. And those units turn out to be kilogram meter squared per second squared. Kilogram meter per second squared. That's a Newton. That's a Newton squared. And kilogram meter per second squared. Yeah, it's Newton squared. And all that divided by 6.5 times 10 to the 4th newtons per meter. So ultimately, we see we're going to get just units of meters. The square root of 2,000 of this big number is obviously really big. So we're going to say 955 plus or minus. That gives me 167,450. Actually 451 newtons. And obviously all those are made up sig figs. Divided by 6.5 times 10 to the fourth newtons per meter. So obviously we can see that the negative doesn't make any sense. So we're going to have to take the positive one, which is the adding of the two instead of the lower one. So we'll say this number plus 9555, which really only has a sig fig at the thousands. So this really should be about 1.77 times 10 to the fifth newtons per 6.5 times 10 to the fourth newtons per meter. And I'll circle this just to remind you I'm only using that one. Now I'm going to divide this by 6.5 e to the fourth. And that gives me 2.723 meters.
Thank you.
Did that help?
Yes, thanks.
No problem. Yeah, that should work. You always got to watch out for things like that. That one's real easy to try to mess up just because you think of the U as being 0 at the top of the spring, but then you're missing part of the kinetic energy or part of the potential energy that's still left just due to gravity. And I would have on first thought that delta X would be small compared to everything. And it's, it's on the order of what, 10%. So it's not that small. Anybody else have anything? We still got a couple more minutes before we start back. All right. So it does look like it's time to go ahead and get started. Anybody have any questions before we get cracking? This is the lab portion. It's going to be fairly short. Let me stop sharing for just a second and open up our Moodle page, excuse me, not Moodle, our Canvas page. So I'm going to go to the modules. And this time I'm going to try to open up the lab document that I just posted on week 7. Hopefully it'll open, easy peasy. Okay, yeah, this looks good. So this is a document I wrote some time ago. I was, as chair, I was trying to make sure we started making our labs a little more consistent with UVA, Virginia Tech, Chapel Hill, NC State, those types of places, where basically students are learning, even in the algebra-based physics, they're learning propagation of error instead of just blindly applying sig fig rules, which is, mostly what we do in lab, and a lot of labs still do that to this day, but it's it's not good. Okay, that is not the way that real scientists deal with numbers. And the big problem is this: if you make a measurement, every measurement has some sort of error associated with it. And you have to be knowledgeable of how big that error is. And you've got to be honest about reporting that to whoever's reading your work. So what happens then if you are using some measured quantities with measured error and you're doing calculations with them? How much error does that final answer have? That's the big question. And that is what we talk about when we say error propagation. It turns out that the methods that I taught you about about significant digits is okay, but there's literally times where it's absolutely horrible. So if you look on some of the videos I have listed in my Canvas page, as well as just on my YouTube channel, one of them is when sig figs goes wrong. So that's a good introduction. You should watch all those, in fact, but this document is what you're going to do. I'm getting ready to explain it. And then this is it explained in words. The main thing you got to remember is that there's something in statistics that we call the standard deviation. There's also another thing in statistics that we call the standard error. And the standard error is often called the standard deviation of the mean. And there's something very special about those. It turns out if your errors are really, more or less at random, then if you consider everything that's one standard deviation from, well, let's back it up a second. Okay, so let's say we're doing a measurement in a lab, and in the lab we're measuring some distance x, and we get, the quantity like I wrote on this sheet a second ago. Let's say we got the quantity x was 3.42 plus or minus 0.03 centimeters. What does that tell me? Well, what that tells me is if a million different labs tried to do the same thing, then basically 68.1% of them would find an x between 3.42 minus 0.03, which is 3.39, and 3.42 plus 0.03, which is 3.45. So 68% or 68.1%. I'm writing this on my tablet, and I'm going to show you the tablet in a second. So 68.1% of measurements made in the 1 million labs will be between X bar minus S sub X and X bar plus S sub X. Now, additionally, so I was saying if you had let's say 100 million, that way it's a factor of 100 that's helpful. So let's imagine having 100 million labs. If we had 100 million laboratories, and each of those laboratories measured the quantity X of that little block I drew a second ago, and they found the quantity to have some value plus or minus some error. Okay. If we actually use the standard deviation for that error, then what we know is 68 of the 100 million, 68,100,000 of them would fall between the mean and one standard deviation. 95.4% or 95,400,000 would be between the average minus 2 standard deviations and the average plus 2 standard deviations. And finally, the last part is 99,800,000 would fall between X minus 3 standard deviations and X average plus 3 standard deviations. Okay, so the standard deviation is a measure of how other experimenters would come up with a value that they're also measuring. Now that is helpful, that tells us something, but it's not what we really want. What we'd really like to know is what would 68.1% or 95.4% or 99.8% come up with as their final value of X, not a particular trial of X. In that case, you have to do the standard deviation of the mean, and that's called the standard error. And it has the same properties as the standard deviation, and it's actually differs in calculation by just one little step. You take the standard deviation, you divide it by the square root of the number of trials, and you get the standard error. So that's the big point here. Now, this document goes over all that stuff. It's something that you should read thoroughly and read it really like it's a really important thing. Read it, try to understand it, get these rules out of it, and then you're going to, in fact, not this particular table, but you'll see down in the question parts, there's the same table drawn there. You're going to fill all that out. Okay. Notice all these formulas, they look kind of scary, right? They're not that hard though. So here's the propagation of error formulas. When I get down here, here's the question. Show that for f of x equals x plus y, show that this is the case. For x minus y, show that I get the same case, and so on and so forth. And then it says, fill in these. So here's your h's. The h bar is one way we express a mean. So literally, if you took and added all these up, you'd put them right here where it says sum. And then you divide it by 1, 2, 3, 4, 5, 6, and put that right here. That's the average. So then you do 56.4 minus whatever that average turned out to be. And there's all sorts of hints to what those answers are in the paragraphs above. You put that here. And then you do the same thing with 56.38 minus the average, put that here. And then once you fill up that column, you square this one, put it here, 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 square this one, put it here. And then when you're all done, you can add up all those, and what you'll have is this numerator right here under the square root. In other words, when you take these 6 quantities and add them together, you'll have the summation from I equals 1 to 6 of h minus h bar squared. Now you're going to divide that by 5, which is n minus 1. It's the number of trials minus 1. And then you're going to take the square root of it, and that answer goes right here, and that is the standard deviation. If you want the standard error, all you do then is take this number, which will be right here, and divide it by the square root of 6, and that'll be your standard error, and that's what goes here. Okay, so this is what your job is. I will give you until Monday of next week to turn this in, but first I need to go over it, and I just wanted to show you where it is and how to download it, and where you download it, and all that good stuff. So let's stop sharing. Does anybody have any questions about this document? I'm getting ready to do all the explanation that's in these paragraphs, but hopefully a little easier because it's the spoken word. No questions? All right, we'll stop sharing that then. Okay, so here's a shot over the bow to get you thinking about what I'm talking about. So propagation error. Let's imagine you take a little aluminum block, and that little aluminum block is not unlike the little aluminum block we did to measure density of aluminum some time ago in lab. Y'all probably remember that, hopefully. But you can take vernier calipers, for instance, and measure it. And with those vernier calipers, you're going to have an error associated with of at least 1 in the last decimal place. But when you're all finished with it and you take many, many trials, partly because, you know, for instance, a given dimension should be fairly straight. Like if we're looking at the distance x, which is the distance from the front to the back, that distance x at this right hand side might be slightly bigger than it is at the left hand side. There might be dents in it. There might be just bad manufacturing. All sorts of different things could happen. So ideally what you'd want to do is you take that measurement of x and you write it down, and then you put your vernier calipers on another random spot measuring x and write that down, and keep doing that over and over and over again. As many trials as you could possibly do, the more you do, the better, right? When you do all that, then your best estimate of what x is really the average of all those. So you take all those maybe, you know, 3.42, 3.4, 3.41, and by the way, 3.4 is the same thing as 3.40, but you have to list it as 3.40 in your lab. Anyways, 3.41, 3.42, 3.44, all those different things, you add them all up. If you actually knew that some of them had more error than others, you could actually do a weighted average instead, but we're not going to make you do that. I just wanted you to know it exists. But the main thing is you would take an average, and that average would be the best estimate for that value of x. Okay, so the average of your data, or if you can do it, the weighted average is even better. Okay, but that's your best bet, or your best estimate of any value is the average of all the trials. Then when you did that, if you then take and calculate the standard deviation, and then using that standard deviation calculate the standard error, then the standard error is what's supposed to come after the plus or minus. Okay, now if that standard error was actually smaller than the error in the instrument, so for instance, I told you it's vernier calipers, they have at least an error of 0.01, in other words, 1 in the last decimal place. So if they had an error of 0.01 and you got 0.009 or 0.006 or something, then you'd have to throw that out and use the instrumental error, because you cannot use statistics to eliminate an error that's built in, right? The error was literally built in specifically because of the instrument we use, so it's not going to just disappear by doing statistics. So that's a golden rule, is you always have to calculate your standard deviation, and then from that calculate the standard error. But under no circumstances do you use the standard error if the standard error is smaller than the instrumental error. If you're doing using a digital device to measure something, then you can assume it's 1 in the last decimal place. If you actually have the manual, they might express that it's bigger than that. You need to check the manual if you have access to it, but always assume at least a 1 in the last decimal place with digital displays as well. Okay. So now that we have this drawing and I've given you some idea of what these standard deviations and standard errors are like, the question that I'm hoping to motivate you into thinking about propagation error is, okay, I have an X that clearly has an error associated with it. I have a Y that clearly has some error associated with it. And I have a Z and that clearly has some error associated with it. Now I'm going to calculate the volume of this thing. Well, the volume is X times Y times Z. So what will the error in the volume be? That's the big question. So when you do that, one of the things you might consider, and I've done this myself several times, you might consider V big, in other words, the biggest possible volume that you'd have would be X plus sigma X. That, by the way, is the symbol for standard error. F sub X is standard deviation. And sigma sub X is standard error. Okay, so like that. So the biggest you'd expect the volume to be is when you use the biggest X, the biggest Y, and the biggest Z. And the smallest would be X minus sigma X times Y minus sigma Y times Z minus sigma Z, like that. That's going to be 3.45 centimeters times 7.96 centimeters times 1.05 centimeters. So when I multiply those, 3.45 times 7.96 times 1.05, I get 28.8351. And that's centimeters cubed. Okay. I should probably make that a little easier to see. No, it looks good, at least at that size. I have no idea what it's going to look like over there. Okay, so that's what I mean by the biggest possible. Now, the smallest possible would be 3.39. I want to leave off the units this time, just for space. The Y is 1.01 minus 0.04, so that'd be 0.97. And then the 7.89 minus 0.07 is 7.82. Okay, when I multiply those, you get 3.39 times 0.97 times 7.82. That gives me 25.7145. So that's the smallest volume I could see plausible. So if I actually wanted to express the volume as some number plus and minus a number, then what I should do is find out basically how far those two numbers are away from each other and then divide it by 2. So if I do V big minus V small and divide it by 2, I can sort of treat this as like, I'm going to put quotation marks around it because it's not using the actual standard error formula. I could say sigma V might be approximately this. So now I'll take 28.8351 minus the answer I just found, and I get 3.120594. I divide that by 2. I get 1.560297. Notice I'm not making any attempts to round off. I'm literally putting all the numbers that the calculator gave me because I don't know where to round off. In fact, what I do know is that if my uncertainty, for instance, in X is 0.03 centimeters, then any digit beyond the 2 in that 3.42 is definitely unknown because I don't even know that third figure, the 3.42. I don't know the 2 to within plus or minus 3. So it could be as high as 3.45 or as low as 3.39. So it makes no sense whatsoever to add a decimal beyond that. So that's sort of our guiding principle is, well, I can only have really one doubtful digit, and that doubtful digit needs to be the very end of the numbers. So right now I can see my doubtful digit is doubtful in the whole numbers at least. So I might say V is equal to what I really want is the best estimate, and that's the 3.42 times. So V best is 3.42 times 7.89 times, again, I'm leaving off the units on purpose just to give me some room. 3.42 times 7.89 times 1.01. That's going to give me 27.25. 253638 cubic centimeters. So it looks like I'm going to have a 1 in the ones place, actually a 2 since the next digit is 5. So I'm going to say 27 plus or minus plus or minus 1 cubic centimeter. That's the way I would report it if this is really the proper way to analyze it. It turns out this is way overestimating our uncertainties, okay? But that is at least a shot over the bow of what we might think is a approximately correct way to analyze this. We have a series of values, X, Y, and Z. Each of them have an error, sigma X, sigma Y, sigma Z. And we don't expect the majority of other experiments to find any numbers outside of those X's, Y's, and Z's within their range. And we therefore expect the volume to be probably 27, as small as 26, but as big as 28 cubic centimeters. Okay. But it turns out, like I said, the method is a lot easier than that. Here's the argument for it. So we have a value right now. We figured out a value. We've also figured out that, hey, we're going to round our result to the same decimal place as the first digit in the error is. And then that way we'll know exactly where to round it. We're not going to use sig fig rules. We're going to keep a bunch of digits until then. But what is the proper way? Well, it's not that. As I said, that did not turn out too well, so we're not going to we're not going to use that method. It turns out though, just like if you imagine a graph of a function, let's say like, whoa, let's say a function like this, here's x, here's y equals f of x. You have a curve like this. Let's say down here you have an x, and then you go out and amount x plus sigma x, say. Actually, let's make it a different symbol. I'm going to say x plus sigma x and put that right there. And then I come back here. What I see is this is f of x, and this is f of x plus sigma x. Okay. So that tells me maybe, just maybe, the sigma f should be equal to f of x plus sigma x minus f of x divided by x plus sigma x minus x, which turns out to be df over dx absolute value bars times sigma x. In fact, if we take the limit as delta x approaches infinitely small, in other words, we can actually get that sigma f is equal to the absolute value of f derivative with respect to x times sigma x. So that's when you have a function of one variable. When you have a function of one variable, in other words, a f that's only a function of x, then the proper way to find out the error in f is you take the error in the x and you multiply it by the derivative of the function. And if you wish to generalize that, in other words, generalize to a function of many variables, what it becomes is this. The uncertainty or the error or the propagated error of the function is equal to the square root of the sum of the squares of, we're going to take the derivative of f with respect to x, acting like all the other variables are constants. And I'm going to square that and multiply it by the uncertainty in x squared plus partial of f with respect to y. Again, that's just like taking the derivative, pretending like all the other variables are constants, times sigma y squared plus partial f with respect to z squared sigma z squared plus dot 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 for however many variables you have. That's the whole formula. That's the error propagation formula. It's very important. If you're lucky enough to just do one variable, then you can just use that derivative one. That works out pretty nice. Like, for instance, our x was equal to 3.42 plus or minus 0.03 centimeters. If I want to convert that to meters, then the formula F is equal to X times 1 meter per 100 centimeters is my function. Okay, it's a linear function, goes straight through the origin. In fact, it looks like that. That's F centimeters to meters. Just looks like that. Okay. So I can say, therefore, the uncertainty in F is equal to the absolute value of 1 meter per 100 centimeters times the uncertainty in X, which is 1 meter per 100 centimeters times 0.03 centimeters, which equals 0.0003 meters. Okay, so that makes sense, and that's obviously a straightforward problem to do, but that's just using that first formula, the absolute value of the derivative of f with respect to x times sigma x. But that's how you use it, and it qualifies. Just converting units is a function acting on a experimental variable. Okay, when you see numbers written like this one is the most probable or the best estimate, and its x bar are a weighted average. Just to give you some background, since I keep mentioning that weighted average, if you had 100 labs working on this and you knew that certain labs are really dodgy and had crappy results, you'd probably know that in terms of how much error they make versus how much error the other labs make. So if you had those error figures for each lab, what you could do is when you take an X from a particular lab, you take that X and you divide it by their uncertainty, because the uncertainty is supposed to be a small number. You divide it by the uncertainty or the uncertainty squared, which it doesn't really matter which one you do. You're taking a bigger effect if you do the squared one, or even bigger still if you do the third one. But you could do 3.42 over 0.09, because this lab is particularly bad, squared. And then you could take another lab's result, which might be 3.41 plus or minus 0.01 or something. So you write 3.41 and divide it by their error squared and sum up all those, and then divide by the sum of all those errors you just did. That would be the weighted average. And by you taking the one, dividing by the errors squared, basically what you've done is you've made the weight be the highest for the lowest errors. So that's how you go about doing that. But again, I'm not going to make you do any of that. I just wanted you to know how it was. So let's look, for instance, at some other examples. Let's do a simple example, like f of x and y is equal to x plus y. Okay. And this is also me taking the opportunity to teach you how to do a partial derivative, which scares a lot of people just to see it, just to be told that, a partial derivative is a thing that you got to do, and you've never learned it in a science class before. That's scary to a lot of people. So you're probably fretting it a little bit, but that's okay. We're going to show you how. All I'm telling you is when you see a partial derivative is you pretend all the variables that are not in the bottom are just constants. So if I take the partial of f with respect to x, you can imagine this as x plus 4. What would be the derivative of x plus 4?
Just one.
1. And that's actually the right answer. That's what you do. You literally just pretend the variable is a constant. Okay, what about this? Now we're going to do the partial of f with respect to y, which is equal to d by dx of, in this case, 13 plus y. So now I'm pretending x is 13 because that's a constant. Anybody who give me the derivative on this one?
It would be the same thing, Professor.
Exactly, 1. So now we have to do is we say sigma f is equal to the square root of 1 sigma x squared plus 1 sigma y squared, which is just the square root sigma x squared plus sigma y squared. So that's the formula that you use when you add two variables. As you can tell, if you add 84 variables, you're just going to get 84 terms, right? So that's it. What about this one? Let's say f of x y is equal to x minus y. Anybody want to give me the partial of f with respect to x?
1.
1. Anybody want to give me the partial of f with respect to y?
-1.
-1. Easy peasy, right? So that means sigma f is equal to square root of 1 squared sigma x squared plus -1 squared sigma y squared. By the way, these other ones are squared too. I just didn't, since it was 1, I didn't even make a point to write it on there. But you can see now, in this case, we got sigma f for x minus y is just equal to the square root sigma x squared plus sigma y squared. And sigma f for x plus y was the same thing. So circle these neat results. They're easy peasy. Let's try to get a little harder though. Let's say f of x y is equal to x times y. So now instead of 4 plus x or 13 plus y, we're going to have 4x or 4y or something like that. So what's the partial of f with respect to x for this guy? You can blurt it out, or you can see if anybody.
Y?
It's y, yes. Because it's just like 3 times y. The derivative of, or excuse me, in this case, it's taking the derivative with respect to x. It's just like 3 times x. And of course, the 3 is representing the y. So when you take the derivative of 3 times x, you just get 3, which is y. So partial of f with respect to y.
X.
X, very good. So this one looks a little worse, but I'll show you something kind of neat by manipulating it a little bit. What I'm going to do is I'm going to say y squared sigma x squared plus x squared sigma y squared. And that's kind of ugly. Right, that's not very pretty, but I can make it look just like that last answer I got for addition and subtraction by doing this. I'm going to introduce something called the fractional error. So fractional error. And that's just the uncertainty divided by the value. So for instance, if I wanted the fractional error of x from that problem right there, I'd do 0.03 divided by 3.42. And that would be 0.00877. that's what the fractional error of x is. So that's all we're talking about, but it literally means you take the error and you divide it by the best estimate of the value. Okay. So now that I've introduced that, I can say sigma f for x times y. Notice I'm writing it for to x times y over f is equal to the square root of y squared sigma x squared plus x squared sigma y squared. But here's the kicker. I'm going to divide by f. And f, of course, is x times y, but I want that to be under the square root. So I'm going to write down here square root, and then I'm going to say x squared y squared. Because if I want to stick something under a square root, then I have to square it first. Now I can make it one ginormous square root, and what you see is I've got y squared sigma x squared over x squared y squared plus x squared sigma y squared over x squared y squared. So we end up getting for multiplication, we get sigma x over x squared plus sigma y over y squared. Because you can see what happens is I've just left with sigma x and x on top of each other. So the fractional error of a function that is the product of x and y is equal to the sum of the squares of the fractional errors. Let's try another one. Let's say f of x y is equal to x over y. This is a little harder. Did someone think they can answer what the partial of f with respect to x is?
Just 1 over y.
Yeah, for the x, because this is just like 1 over y times x, and that's just like 1 over 2 times x. So yes, 1 over y. The hard one is the next one. Partial f with respect to y. It's still not that hard though, hopefully. Anybody?
Is it x over y squared?
Negative x over y squared, yes.
Oh, that's right.
You just left off the -1.
Yeah, from the, yep.
Good job. Yeah. All right. So now I'll put this in and I get something even uglier, but watch again, doing the fractional error will save me. So I'm going to say, start back writing in blue, sigma f x over y is equal to square root. Now I'm going to say 1 over y squared sigma x squared plus x squared over y to the 4th sigma y squared. That is ugly, but now I'm going to say sigma f for x over y over f is going to be a ginormous square root. I'm going to say sigma x squared, and I'm going to say y squared's in the bottom. But now I'm going to have an x squared down here and a y squared up here, because x over y in the bottom, once you put it under a square root, becomes x squared over y squared in the bottom, which is the same thing as y squared over x squared in the top. Same thing's going to happen over here. I got an x squared sigma y squared over y to the 4th. But now I've got a x over y. In this case, I had an x squared already and a y to the 4th already. Now I'm going to put in a y squared, x squared. like that. And you see that in this case, the x squares completely cancel out, and luckily 2 of those cancel out. Oops. So I get sigma f, where x over y is f, over f is just equal to sigma x over x squared plus sigma y over y squared. Again, the fractional error of the function is equal to the sum of the squares of the fractional errors of the variables. That turns out to be the case whether it's x over y, y over x, xy over z, xz over y. All those different things all add up to give you the same sort of stuff here. You can show that yourself. In fact, that's sort of what the sheet asks you to do, is do these same calculations and others with that. So does anybody have any questions on that? Now that we have that, let's examine our example V of x, y, z is equal to x bar, y bar, z bar, which we already calculated was 27.253638. No, it's 27.253638, I think. 27.2536, I think. So that's our best estimate. Now I want to calculate sigma V. In this case, I know that it's a product, so I really know probably the best thing to do is to calculate sigma V over V. So I could show this already, but I know for a fact that sigma V over V is equal to sigma X over X squared plus sigma Y over Y squared plus sigma Z over Z squared, like that. So I'm going to say sigma V over V is actually equal to the square root. Now X was 0.03 centimeters over 3.42 centimeters. That quantity is going to be squared. Make sure I got the right figures. 3.42, 0.03, 7.89, 0.007. I'm going to add those, and now I need the Z one, which is 1.01, and I think I said 0.02, no, 0.04. 0.04 over 1.01 centimeters. Notice all the units are canceling out. Fractional errors do not have units. They can't, because their units are dividing each other out. So in this case, I'm going to get equals the square root 0.03 divided by 3.42 squared is 7.695 times 10 to the negative fifth plus 0.07 divided by 7.89. And this is 7.8712 times 10 to the negative fifth. And that's already squared, by the way. I put it in parentheses anyways, but it's already squared. 0.04 divided by 1.01 Now I square that and I get 0.0015685. Okay, that's what all those numbers are and squared. So I'm going to say plus 7.695 e to the negative fifth plus 7.871 e to the negative fifth. So I get all of this equals the square root of 0.0017241. Now I'm going to take square root of that. And that gives me 0.041523. Again, I'm carrying way extra digits so you can verify that you did the same calculations and all that stuff with me. Now I've got sigma v, but I've got fractional error of v, which is sigma v over v. And to get the actual sigma v, all I have to do is use the formula. Sigma v is going to be equal to sigma v over v times just plain v. So now I'm going to do is take this 0.041523 and multiply it by the 27.253638 cubic centimeters. Notice that also gives it the proper units. So I'm going to say times 27.253638. That gives me 1.1316 cubic centimeters. So last time we had something that had to round up to 2 because it was like 1.5 something. This time we have something that rounds to 1 at least, so it's better. All of this allows us to conclude that the appropriate answer to return the final report should claim the volume to be V equals 27 plus or minus 0, or excuse me, plus or minus 1 cubic centimeter.
Professor, in both cases, why do we round off to the 1? What was the reasoning?
Okay, so you understand that every number has a certain error, and every number in fact has one digit that has the biggest error of all of them, and that's the rightmost digit. So if 27 has an error of plus or minus 1 in the ones place, which is what we just found, then we have no hope whatsoever of knowing what the tenths place is, or what the hundredths place is, or any of those. So basically the whole round off process is hinging on the fact that there's exactly one doubtful digit, and that doubtful digit lines up with the biggest digit in the error. Occasionally people might use 2 digits for the error. Like I might say 1.1, and if I did that, I would call it 27.3 plus or minus 1.1, so that the last digits still line up. But to be honest with you, the only time you should ever use more than 1 sig fig in that after the plus or minus symbol is when it's like 1.3, 1.4, 1.5, 1. Stuff like that, because in that case where you have 1 as the front digit, the 3 or the 4 is a huge fraction of the 1. So they tend to do it for that reason and that reason only.
So that was what I was gonna say, because before we had 1.56 as our sigma v in the previous example. And
Right.
we rounded down instead of like I thought you would round up, you know.
Oh, that one I should have rounded up. Did I not call it 2?
I think you said it was 1 instead of 2.
Oh yeah, I did write down 1. It's definitely supposed to be 2. You're right on that.
All right. No, I just trying to understand what's going on here.
Yeah, that's because it was 1.56. Yeah, I don't even know why I wrote this. I knew it was 2. I didn't even realize I wrote that. But yeah, that's definitely supposed to be 2, everybody. It's in the notes. By the way, remember on your Canvas page, there's a useful documents and links section, and it includes my Google Docs. You can click on that and this will be up there. Notice the name of this file is PHY241D01B, and then it'll have an underscore 07032023, which I think you recognize as July 3rd, 2023. So if you just do a search for that date, 2-digit, 2-digit, 4-digit, you'll find this document. But yeah, definitely make sure it's supposed to be plus or minus 2 cubic centimeters. That was just a screw up on my behalf, writing 1 there. And this one, we always round it to 1 sig fig. Like I said, occasionally you'll see papers where they'll do 2 sig figs on the error. In that case, that it's normally because they're trying to express the fact that the digit after the 1 is a big fraction of the 1. So 1.4, for instance, the 0.4 is 40%. So that's kind of a big deal. If you just throwing out 40% of a number, you feel bad. So we always just make sure the 2 line up. That's the key point of the discovery. And you don't know that they line up until you do error propagation. So we're not using sig figs. All we're doing is using error propagation tools. And I'm just saying this is how the lab should be done. I'm not necessarily going to switch what you have to turn in every week now to include that. I might have a lab or 2 where I ask you to do this instead of the normal thing, but not this time. So anyways, that's it, folks. Let's call it a day. You guys are free to go to enjoy the rest of your vacation. You can download this error propagation. It's a Word document and you can type right into it and do like we normally do with a lab. I want the whole thing turned in. I want you to answer the questions at the end. And I think if you're looking at it, you'll see that I, in fact, did a lot of the work for what you have to do, and you should already know. But if you wait too long to try to do it, you're going to forget all this. So by all means, try to read this soon and do questions 1 through 1 through 9. And turn that in for next week. So have a good one. I'm waiting for the last person to leave before I leave, but you guys are done for the day. Have a good one.
You too, Professor.
Thank you, Aaron. Thank you, Robert. Do you have any questions, Jonathan or Griffin? All right, looks like that's it then. Bye, everyone.